In 2015, a spacecraft the size of a piano flew past Pluto at 30,000 miles per hour. It took 9.5 years just to get there, and it never stopped. It could not stop, because stopping would have required more energy than humanity has ever put into any space mission in history. We talk about reaching Pluto like it is simply a matter of building faster rockets or waiting longer. The truth is far more disturbing. The real barrier is not distance. It is not time. It is not even human endurance. It is something far more fundamental, something that governs every machine, every heartbeat, every civilization. Energy. If you are ready to discover why the edge of our solar system might remain forever beyond human reach, hit that like button and subscribe. This is a journey through physics, engineering, and the uncomfortable limits of what our species can actually achieve. Now, get yourself nice and comfortable. Let's begin. Ask someone how far away Pluto is, and they will probably give you a number. Maybe they remember it from a documentary or a classroom poster. 3 billion miles, 4 billion, something enormous, but ultimately just a number on a page. The truth is far stranger. Pluto does not sit at a fixed distance from Earth. It dances through an elliptical orbit that takes 248 Earth years to complete. At its closest approach, called perihelion, Pluto swings within 2.7 billion miles of the Sun. At its farthest point, aphelion, that distance stretches to 4.6 billion miles. The difference between Pluto's closest and farthest positions from Earth exceeds 2 billion miles. This orbital eccentricity means that the question of reaching Pluto has no single answer. The journey length depends entirely on when you launch and where Pluto happens to be in its glacial orbit around the Sun. Miss your optimal launch window, and you might add years or even decades to your travel time. The mathematics of orbital mechanics transforms what seems like a simple distance calculation into a problem of cosmic geometry, involving two moving targets tracing complex paths through three-dimensional space. Pluto last reached perihelion in 1989. It will not return to that closest point until 2237. For the next several decades, our target drifts ever farther from the Sun, making an already impossible journey progressively more difficult with each passing year. Anyone planning a Pluto mission today faces a target that grows more distant with each orbit. Earth completes around the Sun. The orbital mechanics create another complication that mission planners must consider. Earth and Pluto do not move in the same plane. Pluto's orbit tilts 17 degrees relative to the plane where most planets travel. This inclination means that reaching Pluto requires not just traveling outward, but also climbing or diving relative to the solar system's main disk. Changing orbital planes costs additional energy, adding to an already overwhelming propulsion burden. Consider what humanity has actually accomplished in reaching distant worlds. The Apollo missions traveled roughly 240,000 miles to reach the Moon. That journey took approximately 3 days. The astronauts packed food for a week, carried oxygen for their breathing and their fuel cells, and relied on solar power and battery reserves to run their spacecraft systems. They remained in constant radio contact with Earth, with communication delays measured in mere seconds. The Moon mission succeeded partly because of their brevity. 3 days of travel meant 3 days of consumables, 3 days of life support, 3 days of potential equipment failures to guard against. The astronauts could carry everything they needed for such a short expedition without overwhelming the spacecraft's mass budget. Mars presents a significantly greater challenge. The red planet orbits at an average distance of 140 million miles from Earth, though this varies between roughly 34 million miles at closest approach to over 250 million miles when Earth and Mars sit on opposite sides of the Sun. Our most successful Mars rovers travelled for between 6 and 8 months to reach their destination. Even these robotic explorers pushed the boundaries of what deep space missions could accomplish with available power systems. The Mars rovers Spirit and Opportunity were designed for 90-day missions. Spirit lasted over 6 years. Opportunity survived nearly 15 years before a global dust storm finally ended its mission. These remarkable lifespans exceeded all expectations, yet they pale against the timescales a Pluto mission would demand. A spacecraft bound for Pluto must function reliably for decades, not months or years. Now multiply that distance by 20, or 30, or 40, depending on orbital positions. The New Horizons spacecraft remains the only human-made object to visit Pluto. Launched in January 2006, it flew past the dwarf planet in July 2015, after a journey spanning 9 years and 5 months. At launch, New Horizons held the record for the fastest spacecraft ever sent into the outer solar system, leaving Earth at approximately 36,000 miles per hour relative to our planet. The mission received a critical boost from Jupiter. By carefully timing the launch window, mission planners arranged for New Horizons to pass close to the giant planet in February 2007. Jupiter's massive gravity field acted as a slingshot, accelerating the probe by roughly 9,000 miles per hour and bending its trajectory toward Pluto. Without this gravitational assist, the journey would have taken several additional years. Gravity assists represent one of the few free advantages available to spacecraft designers. By carefully routing a spacecraft past a massive planet, mission planners can steal a tiny fraction of that planet's orbital momentum and add it to the spacecraft's velocity. The planet slows by an imperceptible amount, while the spacecraft gains significant speed. Jupiter has served as a cosmic accelerator for numerous outer solar system missions, but gravity assists come with constraints. The geometry must align properly between Earth, the assisting planet, and the final destination. Favorable alignments occur only during specific windows that may be separated by years or decades. A mission that misses its optimal launch window cannot simply wait a few months and try again. It might need to wait a decade or more for the planets to realign. But here is what most people miss about New Horizons. That spacecraft never stopped at Pluto. It could not stop. It screamed past the dwarf planet at over 31,000 miles per hour, capturing photographs and scientific data during a flyby lasting mere hours. The encounter window for close observations measured only about 1 day out of a mission spanning nearly a decade. The photographs New Horizons captured revolutionized our understanding of Pluto. The heart-shaped nitrogen ice plain now called Sputnik Planitia, the complex geology of water ice mountains, the thin nitrogen atmosphere, the reddish organic compounds coating the surface. All of this emerged from a brief encounter lasting less than a day after nearly a decade of patient travel. Why did New Horizons not stop and orbit Pluto, like spacecraft orbit Mars or Saturn? The answer introduces the central problem that will haunt every section of this story. Stopping requires energy. Every pound of spacecraft traveling at 31,000 miles per hour carries kinetic energy that must be cancelled out to achieve orbit. This means firing rocket engines in the opposite direction of travel, burning fuel, converting stored chemical energy into thrust. The amount of fuel required to stop New Horizons at Pluto would have exceeded the mass of the spacecraft itself many times over. The mission designers faced a brutal choice. They could send a small, fast probe that would zoom past Pluto and continue into interstellar space forever. Or they could send a larger, slower mission carrying enough fuel to stop, which would have required decades to arrive and might have failed before reaching its destination. They chose speed over arrival because the energy mathematics left no other reasonable option. This brings us to the fundamental equation that governs all space travel. Every spacecraft that moves through the void carries its own energy supply. Usually, this takes the form of chemical propellant stored in tanks. The propellant has mass. Moving that mass requires energy. That energy comes from burning more propellant, which also has mass, which also requires energy to move. This circular trap is called the rocket equation. First derived by Russian scientist Konstantin Tsiolkovsky in 1897, it defines why space travel remains so extraordinarily difficult despite decades of technological advancement. To go faster, you need more fuel. More fuel means more mass. More mass requires yet more fuel to accelerate. The mathematics grow exponentially worse as your desired speed increases. The exponential nature of this relationship cannot be overstated. Linear problems yield to straightforward solutions, need twice the result, apply twice the effort. Exponential problems resist such simple approaches. Need twice the velocity change? You might need 4 times the fuel, or 8 times, or more, depending on your starting point and the efficiency of your propulsion system. For a mission to Pluto, these numbers become terrifying. Imagine you want to send a spacecraft not merely past Pluto but into orbit around it. Your vehicle needs to accelerate away from Earth, travel for years across billions of miles, and then slow down enough to be captured by Pluto's weak gravity. That final deceleration burn might require changing velocity by several miles per second. Pluto's gravity is remarkably weak compared to larger bodies in the solar system. The dwarf planet mass is only about 1/5 of 1% of Earth's mass. Its escape velocity measures roughly 1.2 kilometers per second, compared to 11.2 kilometers per second for Earth. This weak gravity makes orbital insertion easier, in one sense, but provides almost no free assistance in capturing an incoming spacecraft. A vehicle approaching Pluto must do nearly all the work of slowing down, using its own propulsion. The fuel required for such a maneuver does not scale linearly. It scales exponentially. A spacecraft capable of orbiting Pluto would need to carry fuel loads measured not in tons but in hundreds of tons, and all that fuel must itself be accelerated to tremendous velocities and maintained across years of travel through the void. We have not even discussed keeping humans alive yet. Simply getting a robot to stop at Pluto rather than flying past represents an energy challenge that exceeds anything humanity has attempted in space. The distances involved defy human intuition in ways that matter profoundly for mission planning. Light itself, the fastest thing in the universe, requires between 4.5 and 6.5 hours to reach Pluto, depending on where the dwarf planet sits in its orbit. At average distance, roughly 39.5 astronomical units from the Sun, light takes approximately 5.5 hours for the one-way journey. An astronomical unit equals the average distance between Earth and the Sun, approximately 93 million miles. Astronomers use this unit because raw mile figures become unwieldy at interplanetary scales. Pluto orbits at roughly 40 astronomical units on average, meaning light from the Sun takes over 5 hours to reach it. When New Horizons sent photographs back to Earth during its flyby, mission controllers waited hours for each transmission to arrive. Any command sent to the spacecraft faced similar delays. Radio signals and light share the same speed limit, approximately 186,000 miles per second. At Pluto's distance, this creates communication delays measured in hours rather than seconds or minutes. A conversation with astronauts at Pluto would require waiting 10 or 11 hours between asking a question and receiving the answer. In an emergency, ground controllers could not provide real-time assistance. Any crisis would need to be resolved by the crew alone, with help arriving almost half a day later. Compare this to the Moon, where communication delays measure roughly 1.25 seconds each way. Apollo astronauts could hold near normal conversations with Houston. Questions received answers in moments. Guidance updates arrived almost instantly. The astronauts operated within a zone where Earth-based support remained practically available. Apollo 13 demonstrated how crucial this real-time communication could be. When an oxygen tank exploded en route to the Moon, ground controllers worked frantically with the crew to devise survival procedures. Engineers on Earth could diagnose problems, propose solutions, and guide the astronauts through emergency protocols in near real time. The crew survived because help was only seconds away. Mars stretches this communication envelope considerably. Depending on orbital positions, radio signals require between 3 and 22 minutes to travel between Earth and Mars. This delay already creates operational challenges for rover missions. Controllers cannot joystick a Mars rover in real time. They must send commands, wait, observe results, and send corrective commands. Each action cycle consumes most of an hour. At Pluto, this operational model breaks down entirely. Hour-scale round-trip communication times mean that any time-sensitive situation must be handled autonomously. A medical emergency cannot wait most of a day for diagnostic advice. A propulsion system malfunction cannot wait for ground engineers to analyze data and recommend solutions. The crew must carry expertise sufficient to handle any conceivable problem without external input. But communication delays, while operationally challenging, represent a problem of inconvenience rather than impossibility. Astronauts could be trained for autonomous operations. Mission protocols could account for delayed communications. Artificial intelligence systems might provide real-time decision support. The deeper issue involves what those vast distances mean for energy supply. Every space mission requires power. Electricity runs the computers that navigate the spacecraft. It heats the components that would otherwise freeze in the cosmic cold. It powers the radios that maintain contact with Earth. It operates the scientific instruments that give the mission purpose. For human crews, electricity also runs life support systems, air recyclers, water purifiers, and everything else that keeps biological organisms alive in the hostile vacuum of space. Where does this electricity come from? Near Earth, spacecraft rely on solar panels. Our sun produces an almost inconceivable flood of energy, enough to power human civilization thousands of times over if we could capture it all. In Earth orbit, solar panels generate abundant electricity with reliable consistency. The technology is mature, well understood, and continuously improving. Modern solar cells achieve efficiencies approaching 30%, converting nearly a third of incoming sunlight into usable electricity. The first practical solar cells developed in the 1950s achieved efficiencies below 10%. Decades of research have pushed that figure steadily upward. Laboratory cells have demonstrated efficiencies exceeding 40% under concentrated sunlight. Even at Mars, roughly 1.5 times farther from the Sun than Earth, solar power remains practical for robotic missions. The Opportunity rover operated on Mars for nearly 15 years, using solar panels that generated enough electricity for its modest needs. The InSight lander used solar arrays throughout its mission. When dust accumulated on the panels, power dropped, but the basic approach remained viable. The Ingenuity helicopter charges its batteries using solar cells, despite the reduced sunlight intensity on Mars. But sunlight obeys an inverse square law. Double your distance from the sun, and the light intensity drops to 1/4. Triple the distance, and intensity falls to 1/9. This mathematical relationship governs how energy spreads through space, and it shows no mercy to spacecraft traveling toward the outer solar system. The inverse square law emerges from simple geometry. Light radiates outward from the sun in all directions. At greater distances, that same light spreads across larger spherical surfaces. The surface area of a sphere grows with the square of its radius. Therefore, the light intensity at any point drops with the square of the distance from the source. At Jupiter, roughly 5 times Earth's distance from the Sun, sunlight arrives at approximately 4% of its intensity at our home planet. The Juno spacecraft orbiting Jupiter uses solar panels, because modern high-efficiency cells can still generate useful power at that distance, but just barely. Juno's solar arrays span roughly 60 feet in total width to capture enough dim sunlight for the spacecraft's systems. At Saturn, nearly 10 times Earth's distance from the Sun, solar power becomes marginal at best. The Cassini spacecraft that explored Saturn for 13 years relied on radioisotope thermoelectric generators rather than solar panels, because the available sunlight could not power its instruments and systems reliably. The decision was not about preference but about physics. Solar collection at Saturn simply could not meet mission requirements. At Uranus, roughly 19 times Earth's distance from the Sun, solar intensity drops below 1% of its value near Earth. No spacecraft has orbited Uranus. The Voyager 2 probe that visited in 1986 flew past without stopping, powered by nuclear batteries rather than solar arrays. At Neptune, 30 times Earth's distance from the Sun, conditions grow even more hostile. Voyager 2 visited Neptune in 1989 and continued outward, becoming one of the most distant human-made objects in existence. Its nuclear power source continues generating electricity decades later, though at diminishing levels as the plutonium fuel decays. At Pluto, averaging nearly 40 times farther from the Sun than Earth, sunlight arrives at roughly 1/1500th of its intensity at our home planet. This figure varies as Pluto moves through its eccentric orbit, ranging from about 1/900th at perihelion to roughly 1/2400th at aphelion. But even the most favourable case provides essentially no usable power for spacecraft systems. A solar panel that generates 1000 watts of electricity in Earth orbit would produce less than 1 watt at Pluto. The Sun appears as merely a bright star from that distance. From Pluto's surface, the Sun would appear roughly 250 times brighter than the full moon appears from Earth. Bright enough to cast shadows, bright enough to read by, but utterly inadequate for powering the complex systems that keep spacecraft functioning and humans alive. This is why New Horizons carries a radioisotope thermoelectric generator instead of solar panels. This nuclear battery converts heat from decaying plutonium-238 into electricity through the thermoelectric effect. The heat differential between the hot plutonium core and the cold exterior of the spacecraft drives a small but steady flow of electrical current. The system produces roughly 200 watts of power. 200 watts represents about the same power as 2 standard incandescent light bulbs burning simultaneously. That tiny output sustained a probe weighing roughly 1,000 pounds across a decade of travel through the solar system. 200 watts was enough for New Horizons because the spacecraft was small, its systems were designed for minimal power consumption, and it carried no biological passengers requiring life support. The probe could sleep through most of its journey, with only essential systems running. Then wake up for the brief encounter at Pluto. It did not need to heat a living space or recycle air or purify water or provide lighting for human activities. Now imagine the power requirements for a crewed spacecraft. Multiple humans, breathing, eating, drinking, generating body heat, producing carbon dioxide, requiring climate control, needing light to see, wanting communication with home, depending on navigation systems to find their way. Add their food storage and preparation systems, their water recyclers, their air processors, their waste management systems, their medical equipment, their exercise equipment to prevent bone and muscle loss in microgravity, their psychological support systems for the crushing isolation of deep space. The numbers escalate into territory that makes mission planners pause. Consider the International Space Station, humanity's most sustained experience with keeping humans alive in space. The ISS solar arrays generate approximately 120 kilowatts of electrical power at peak output when fully illuminated by direct sunlight. This supports a crew of typically 6 astronauts in low Earth orbit. 120 kilowatts represents 600 times the power output of New Horizons. Yet the space station barely provides adequate power for its crew of 6. Systems occasionally need to be powered down to conserve electricity. Experiments compete for available power slots. The station operates near the margins of its electrical capacity, despite those enormous solar arrays. But the space station enjoys enormous advantages that a Pluto mission would lack entirely. It orbits close enough to Earth that resupply missions arrive every few weeks, bringing fresh food, replacement parts and new equipment. It receives full-strength sunlight during orbital day, storing energy and batteries for the brief orbital nights. If systems fail critically, crew members can evacuate to Earth within hours using attached spacecraft. A Pluto mission would require similar or greater power levels but could not rely on solar collection and would receive no resupply missions for the entire journey lasting decades. Every watt of electricity would need to be generated internally, either through nuclear reactors or by converting stored fuel into power. Every system failure would need to be repaired using only materials carried aboard from the beginning. Every component would need to function reliably for far longer than any space system has ever operated. The energy demands cascade outward in every direction. Propulsion requires energy to accelerate and decelerate the spacecraft. Life support requires energy to recycle air and water, to heat or cool the cabin, to grow or prepare food. Communication requires energy to transmit signals across billions of miles. Navigation requires energy to track position and course. Scientific operations require energy to power instruments and collect data. And all of this energy must be produced continuously for years, possibly decades, far from any possibility of help or resupply. This brings us back to the original question, reframed through the lens of physics rather than simple distance. How long would it really take to reach Pluto? The honest answer depends almost entirely on how much energy you can bring along and how efficiently you can use it. Travel time trades directly against fuel consumption. Faster trips require more acceleration, which demands more propellant, which adds mass, which requires still more propellant in the exponential spiral of the rocket equation. The fastest conceivable trip using current or near-term technology might achieve Pluto in 4 to 6 years, with a robotic probe carrying minimal mass and making no attempt to stop at the destination. New Horizons demonstrated this approach, though it required a favourable planetary alignment that allowed a gravity assist from Jupiter to boost speed. Such alignments occur only during specific launch windows separated by years or decades. A crewed mission presents fundamentally different constraints. The spacecraft must carry life support systems, consumables for the journey, and enough structural mass to protect the crew from radiation and provide living space. Shielding, air, water, food, medical supplies, spare parts, and all the equipment needed to sustain human life for years would multiply spacecraft mass by factors of 10 or more compared to a robotic probe. More mass requires more fuel. More fuel requires more time, unless you carry even more fuel, which adds more mass, which extends the trap further. A crewed mission might require 15 to 20 years in each direction, using high-efficiency propulsion systems that do not yet exist in flight-ready form. Round-trip missions push toward half a century. Launch when astronauts are in their 30s, and they return as elderly citizens if they return at all. The journey itself would consume the majority of a human lifespan. Children born on Earth at departure would reach middle age before the crew returned, but journey time represents only part of the challenge. Throughout those years and decades, the spacecraft must generate enough power to keep its systems running and its crew alive. Every day of travel consumes energy reserves. Every week depletes the fuel that might otherwise provide propulsion. The longer the journey, the more energy you need, which adds mass, which slows you down, which extends the journey, which requires more energy. This is the trap that makes Pluto so formidable. Distance creates time. Time demands energy. Energy requires mass. And mass extends distance. The variables interlock in ways that resist simple solutions and punish optimistic assumptions. We have rovers on Mars powered by solar panels and radioisotope generators. We have probes orbiting Jupiter and Saturn that relied on nuclear batteries to operate in the dim outer reaches of the solar system. But these missions required years of travel for robots that demanded only modest electricity and carried no biological passengers with their relentless metabolic requirements. A crewed mission to Pluto would represent a jump of orders of magnitude in energy demand, complexity, and duration. It would push beyond anything humanity has attempted in space, beyond anything our current technology can realistically support, beyond perhaps anything our technology will ever support. Yet discussions of reaching Pluto often treat it as merely a harder version of reaching Mars. Add more fuel, wait longer, build bigger spacecraft, scale up the systems that work for shorter missions. The fundamental nature of the challenge gets lost in optimistic assumptions about future technology solving current problems. This brings us to the uncomfortable truth that will echo through every remaining section of this story. The barrier to reaching Pluto is not willpower, it is not funding, it is not political attention or public interest or the courage of astronauts willing to make the journey. The barrier is energy itself, the fundamental resource that makes all action possible. The currency that physics demands for every motion through space. At the distances we are discussing, energy demands grow beyond what our technology can currently deliver. They may grow beyond what our technology can ever deliver, using methods we understand today. The problem is not that we need better engineering, though we certainly do. The problem is that physics imposes constraints that engineering cannot circumvent. The sections that follow will examine exactly why this is true. We will explore every propulsion technology humanity has developed or imagined, and show how each one ultimately fails against energy constraints. We will calculate the power requirements for keeping humans alive in the outer solar system, and discover numbers that dwarf our current capabilities. We will follow the math to its logical conclusion, and confront what it means for human ambitions beyond our immediate cosmic neighborhood. The distance to Pluto spans billions of miles. The time to travel there spans decades. But the true measure of that gulf is counted in watts and joules, in fuel tanks and power generators, in the fundamental currency of physics that governs what anything can do anywhere in the universe. Energy is the real distance to Pluto. And that distance may be greater than we can cross. Every rocket engine ever built operates on the same basic principle. You throw mass in one direction, and the reaction pushes your spacecraft in the opposite direction. Newton's third law, unchanged since the 1600s, the specific methods vary enormously, from the chemical explosions of traditional rockets to the gentle ion streams of electric propulsion. But the underlying physics remains constant across all designs. This constancy means that every propulsion system faces the same fundamental constraint. To accelerate a spacecraft, you must expel propellant. That propellant has mass. That mass must itself be accelerated along with the rest of your vehicle until the moment you expel it. And carrying that propellant requires either more propellant to push it or acceptance of reduced performance. The rocket equation captures this relationship through exponential mathematics. Doubling your desired velocity far more than doubles your required fuel. The relationship curves upward with increasing steepness, eventually reaching points where no practical amount of propellant can achieve the needed speed. Engineers sometimes call this the tyranny of the rocket equation. The word tyranny is chosen deliberately. The mathematics rule absolutely. They cannot be negotiated with, appealed to, or circumvented through clever design. Every propulsion system ever conceived must operate within the boundaries the equation defines. Chemical rockets represent humanity's most mature propulsion technology. We have launched thousands of them over more than 8 decades of development. They carried humans to the moon and robots throughout the solar system. Their performance characteristics are thoroughly understood, their engineering refined through countless iterations and improvements. A chemical rocket works by combining fuel and oxidizer in a combustion chamber, producing hot gases that expand through a nozzle at high velocity. The energy comes from breaking and forming chemical bonds, releasing heat stored in molecular structures. Common propellant combinations include liquid hydrogen and liquid oxygen, kerosene and liquid oxygen, or various solid propellant mixtures. The chemistry of rocket propellants has been exhaustively studied. Researchers have tested thousands of potential propellant combinations, searching for higher performance. Exotic compounds containing fluorine, boron, and other reactive elements have been evaluated in laboratories and test stands. Some of these combinations proved too toxic to handle safely. Others were too unstable for practical use. A few offered marginal improvements over conventional propellants, but introduced handling difficulties that outweighed their benefits. The fundamental limit of chemical rockets lies in the energy density of chemical bonds themselves. This is not an engineering problem. Waiting to be solved, it is a property of physics at the atomic level. No known chemical reaction can release more than a certain amount of energy per unit mass, because the electrons in chemical bonds can only store so much potential energy. This places an absolute ceiling on how fast exhaust gases can exit a rocket engine. The best performing chemical propellants produce exhaust velocities of approximately 4 to 4.5 kilometers per second. Hydrogen and oxygen reach the higher end of this range. Exotic combinations might squeeze out marginal improvements, but no chemical reaction can substantially exceed these figures, regardless of how clever the engineering becomes. The speed of exhaust gases matters because it directly determines propellant efficiency. Higher exhaust velocity means more momentum transfer per unit of propellant consumed. The technical term for this relationship is specific impulse, measured in seconds. Chemical rockets achieve specific impulses of roughly 400 to 450 seconds with the best propellant combinations. This velocity limit directly constrains how much speed a chemical rocket can add to its payload. Reaching Pluto requires velocity changes measured in tens of kilometers per second when you account for escaping Earth's gravity, transferring to a trajectory toward the outer solar system, and decelerating enough to stop rather than fly past. Each required velocity change multiplies through the exponential mathematics of propulsion, demanding geometrically more propellant. The numbers for a crewed mission cascade into impossibility. A spacecraft capable of carrying humans to Pluto and stopping there might require propellant loads exceeding 95% of its total launch mass. For every kilogram of useful payload, including crew, life support systems, and scientific equipment, you would need 20 or more kilograms of chemical fuel. The mass ratios worsen dramatically if you want to return home. A round-trip mission doubles the velocity change requirements because you must decelerate at Pluto and then accelerate again for the return journey. The exponential nature of the mathematics transforms this doubling into propellant requirements that grow by factors of 10 or more. Building such a vehicle strains the boundaries of material science. Structural components cannot form tanks light enough to contain the necessary propellant while remaining strong enough to survive launch stresses and years of thermal cycling in deep space. Tank walls must resist internal pressure from propellant vapors while weighing as little as possible. Every gram of tank structure represents payload capacity lost to overhead. The vehicle might need to be assembled in orbit from dozens of separate launches, each adding complexity, cost, time, and opportunities for catastrophic failure. On-orbit construction has never been attempted at the scales a Pluto mission would require. The International Space Station took over a decade to assemble from modules launched separately. A Pluto vehicle might dwarf the station in mass and complexity. Even if construction challenges could somehow be overcome, chemical propulsion for a Pluto mission would require flight times spanning multiple decades. The mathematics simply do not permit faster travel without fuel requirements that exceed what any conceivable spacecraft could carry. This brings us back to the real issue. Chemical rockets fail for Pluto, not because of engineering shortcomings that might be corrected with better designs. They fail because the energy locked in chemical bonds cannot propel massive spacecraft to the velocities needed for reasonable journey times across billions of miles. Chemistry itself imposes the limit. Ion propulsion offers an alternative approach that initially seems far more promising. Rather than burning chemical propellants in violent combustion reactions, ion engines use electrical power to accelerate charged particles to extremely high velocities. A typical ion engine expels xenon ions at speeds exceeding 30 km per second, roughly 7 times faster than the best chemical rocket exhaust. The physics of ion acceleration differs fundamentally from chemical combustion. Strong electric fields strip electrons from xenon atoms, creating positively charged ions. Additional electric or magnetic fields then accelerate these ions to tremendous velocities before expelling them from the engine. The energy comes not from chemical bonds, but from whatever power source generates the electricity that drives the acceleration process. Higher exhaust velocity translates directly into dramatically better fuel efficiency. The same amount of propellant produces far more total velocity change. Missions using ion propulsion can achieve performance that chemical rockets cannot match using any amount of fuel. Specific impulses of 3,000 seconds or higher become achievable, nearly 10 times better than chemical alternatives. NASA's Dawn spacecraft demonstrated this capability on an actual deep space mission. Dawn orbited both the asteroid Vesta and the dwarf planet Ceres during a single mission, a feat that would have been physically impossible for a chemical rocket of comparable size. The spacecraft's ion engines operated for a cumulative 5.9 years of thrust time, gradually building velocity through patient, continuous acceleration. The Dawn mission illustrated both the strengths and limitations of ion propulsion. Over its 11-year mission, Dawn's 3 ion engines consumed only about 425 kilograms of xenon propellant. A chemical rocket achieving the same total velocity change would have required many times more propellant mass. The efficiency advantage proved decisive for the mission's feasibility. But ion propulsion carries its own fatal limitation when considering a Pluto mission. The thrust produced by ion engines measures in fractions of a newton. The Dawn spacecraft's engines generated roughly 90 millinewtons of thrust at maximum power. This equals approximately the weight of a single sheet of paper resting in your palm on Earth. This gentle push must operate continuously for months or years to build up significant velocity. Ion engines cannot produce the sudden, powerful thrust needed for rapid maneuvers. They excel at patience, at accumulating small advantages over extended periods. But patience costs time, and time at Pluto's distance costs energy in other forms. The Deep Space One mission, which tested ion propulsion technology in 1998, required over 20 months of engine operation to achieve its velocity changes. Scaling up to the requirements for a Pluto mission would demand years or decades of continuous thrust. During all that time, the engine must receive uninterrupted electrical power. More critically, ion engines require continuous electrical power to ionize and accelerate their propellant. The Dawn spacecraft's ion engines demanded 2.6 kilowatts of electricity at full throttle. More advanced designs under development could require 10 to 50 kilowatts. Proposed high-performance systems for interplanetary travel might demand hundreds of kilowatts of sustained electrical input. As established in the previous section, solar arrays become essentially useless beyond Jupiter's orbit. An ion engine at Pluto would need nuclear power, and the continuous electrical demands would require reactor systems far more capable than anything yet flown in space. Those reactor systems add mass. That mass requires propellant to accelerate. The energy must still be supplied somehow, and at the scales needed for a crewed mission, the requirements remain overwhelming, even with efficiency gains. Ion propulsion improves efficiency dramatically compared to chemical rockets, but it transforms the challenge from carrying massive chemical propellant loads to carrying nuclear fuel and complex reactor systems. The energy accounting changes form, but does not disappear. Nuclear thermal propulsion represents another technological pathway that has attracted significant interest since the early days of the space age. In this approach, a nuclear reactor heats propellant directly, typically hydrogen gas, to extreme temperatures. The superheated gas expands through a rocket nozzle, producing thrust with exhaust velocities roughly twice those of chemical rockets. The concept emerged in the 1950s as nuclear technology matured and space ambitions grew. If nuclear reactors could power submarines and aircraft carriers, perhaps they could also power spacecraft. The theoretical advantages appeared substantial. Nuclear fuel contains millions of times more energy per kilogram than chemical propellants. Surely some of that energy density could translate into better propulsion. The United States extensively tested nuclear thermal engines during Project Rover and the Nuclear Engine for Rocket Vehicle Application Program. The program consumed over $1.4 billion in 1960s currency and employed thousands of engineers and scientists across multiple national laboratories. The Nerva engine achieved successful ground tests at full power and appeared ready for flight development before program cancellation ended the work. Test firings demonstrated thrust levels exceeding 200,000 pounds-force sustained for over an hour. The engine achieved specific impulses around 850 seconds, nearly twice the performance of the best chemical rockets. Engineers demonstrated that nuclear thermal propulsion was not merely theoretical but practically achievable with 1960s technology. The reactors worked. The engines fired. The performance matched predictions. Technical success did not guarantee programmatic survival. Budget pressures following the Apollo program led to Nerva's cancellation in 1973. The engines that might have carried astronauts to Mars in the 1980s instead became museum pieces and historical footnotes. Recent years have seen renewed interest in nuclear thermal propulsion for potential Mars missions. NASA and the Defense Advanced Research Projects Agency announced plans to demonstrate a nuclear thermal engine in orbit by 2027 through a program called DRACO. Private companies have proposed nuclear thermal vehicles for rapid transit to Mars and beyond. Double the exhaust velocity of chemical rockets means significantly reduced propellant requirements for a given mission. A nuclear thermal vehicle could reach the outer solar system faster or with less fuel than a chemical rocket of comparable size. The technology offers genuine advantages over conventional propulsion for deep space travel. Yet nuclear thermal propulsion does not escape the energy trap either. The reactor requires enriched uranium fuel. That fuel has mass. The hydrogen propellant, even though used more efficiently than chemical propellants, still must be carried along in enormous quantities for a mission to Pluto. Storing liquid hydrogen for years or decades presents engineering challenges that border on the insurmountable. Hydrogen exists as a liquid only at temperatures below -253 degrees Celsius, just 20 degrees above absolute zero. Maintaining these cryogenic conditions requires either massive insulation or continuous refrigeration that consumes continuous power. Even the best insulation cannot perfectly prevent heat leakage into cryogenic tanks. Over months and years, hydrogen slowly warms and boils off. The escaping gas must either be vented to space, losing precious propellant, or recondensed using refrigeration equipment that adds mass and power requirements. Studies of long-duration hydrogen storage suggest boil-off rates of 1 to several % per month with passive insulation alone. Over a 10-year journey to Pluto, such losses could consume the majority of the initial propellant load. Active refrigeration could reduce losses, but would require substantial electrical power throughout the journey. The cryogenic systems needed to keep hydrogen liquid for years of travel add complexity and mass. Insulation blankets, vapor-cooled shields, refrigeration equipment, and associated control systems might add tens of % to the basic tank mass. The overall system mass for a crewed mission remains enormous despite the efficiency improvements nuclear thermal offers. More fundamentally, nuclear thermal engines provide thrust but not electrical power for other spacecraft systems. They convert nuclear energy directly into kinetic energy of exhaust gases rather than into electricity. A vehicle using nuclear thermal propulsion still needs separate power sources for life support, communications, navigation, and all other systems requiring continuous electricity. This reveals a critical distinction that applies across all propulsion technologies. Thrust and sustained power generation serve different functions. A rocket engine can produce enormous thrust for brief periods during major maneuvers, while a separate power system steadily generates electricity for years of cruise operations. A Pluto mission requires both: burst capability for trajectory changes and continuous generation for everything else. Nuclear thermal propulsion addresses propellant efficiency without solving the sustained power problem. The spacecraft still needs tens of kilowatts of continuous electricity throughout a journey lasting decades. That electricity must come from somewhere other than the propulsion reactor, which operates only during thrust phases. Solar sails offer yet another propulsion concept that eliminates propellant entirely. These enormous reflective surfaces use pressure from sunlight itself to gradually accelerate spacecraft. Photons carry momentum despite having no mass. When they bounce off a reflective surface, they transfer that momentum to the sail, producing a tiny but continuous push. The concept dates to the early 20th century when Russian scientist Konstantin Tsiolkovsky and others recognized that light exerts pressure on surfaces it strikes. Science fiction writers embraced the idea decades before technology could implement it. Arthur C. Clarke's 1964 story Sunjammer depicted racing yachts driven by solar sails. The Japan Aerospace Exploration Agency successfully demonstrated solar sail technology with the Icaros mission in 2010. The spacecraft deployed a 14-meter diagonal sail that produced measurable acceleration from solar radiation pressure. Planetary Society's LightSail 2 mission further validated the concept in Earth orbit, raising its orbital altitude using only sunlight pressure. Without propellant, solar sails avoid the exponential mass penalty entirely. In principle, a solar sail can continue accelerating as long as sunlight reaches it, building velocity over months or years of continuous operation. No fuel tanks to empty, no propellant mass to push, just free energy from the sun. The sail material must be extraordinarily thin and light to achieve useful acceleration. Icaros used a sail just 7.5 micrometers thick, far thinner than a human hair. Even at this extreme thinness, the sail's mass limited the acceleration achieved. Larger sails with better mass ratios might achieve higher accelerations, but manufacturing and deploying such gossamer structures presents severe engineering challenges. But as discussed in the previous section, sunlight intensity drops with the square of distance. Near Earth, a large, efficient solar sail might achieve accelerations of roughly 1 millimeter per second squared. At Jupiter's orbit, solar radiation pressure falls to roughly 4% of its intensity near Earth. At Pluto's distance, pressure drops to less than 0.1% of Earth orbit values. A solar sail that provides meaningful thrust near Earth becomes essentially useless beyond Jupiter. The acceleration drops so low that building additional velocity would require centuries. The sail transforms from propulsion system to dead weight, actually creating drag through interactions with the sparse particles of the interplanetary medium. Worse still, solar sails provide no capability for deceleration at the destination. Arriving at Pluto under sail means arriving at whatever velocity you accumulated while sunlight still pushed effectively. The sail cannot slow you down because the weak solar pressure at Pluto pushes away from the sun, not toward your destination. Laser-driven sails attempt to address this limitation by substituting concentrated laser light for diffuse sunlight. A powerful laser array on or near Earth would beam energy at the sail, providing continuous acceleration regardless of distance from the sun. The Breakthrough Starshot initiative proposes using this approach to send tiny probes to nearby stars at significant fractions of light speed. The physics works in principle. Laser light can be focused much more tightly than sunlight spreads naturally. A powerful enough laser could push a sail to tremendous velocities given sufficient time and distance. The Starshot concept envisions gram-scale probes accelerated to 20% of light speed by gigawatt-class lasers. But laser-driven sails face their own energy constraints when scaled to human missions. The laser array must generate enormous power continuously for years, while the spacecraft traverses the solar system. At Pluto's distance, even a tightly focused laser beam spreads across thousands of kilometers due to diffraction limits, requiring even more powerful transmitters to deliver useful energy to the sail. The energy for those lasers must come from power plants on or near Earth. Beaming enough power to accelerate a crewed spacecraft toward Pluto would require dedicated power generation facilities exceeding the output of major cities. The infrastructure costs would dwarf any space mission ever attempted, and like solar sails, laser sails cannot decelerate at the destination without a second laser array waiting at Pluto, which obviously does not exist. Every propulsion technology examined leads back to the same essential problem. Traveling to Pluto requires energy. That energy must be stored in some form and carried along or collected somehow during the journey. Every method of storing or collecting energy creates its own mass penalties, efficiency losses, and practical limitations. Chemical bonds cannot store enough energy density for efficient deep space travel. Nuclear energy offers higher density but requires heavy reactors and faces fuel production constraints. Beamed energy requires infrastructure that does not exist and may never be practical at required scales. The fantasy of propulsion technology solving the Pluto problem persists because each individual technology seems to offer dramatic improvements over its predecessors. Chemical rockets enabled spaceflight. Ion engines improved efficiency sevenfold. Nuclear thermal could double performance again. Solar sails eliminate propellant entirely. Each advance is real, each improvement matters, yet each technology encounters its own fundamental limits before reaching the performance levels needed for practical human travel to Pluto. The improvements accumulate but never quite reach the threshold where the mission becomes achievable. More advanced possibilities exist on paper. Fusion propulsion might achieve exhaust velocities of hundreds of kilometers per second if the engineering challenges of sustaining fusion reactions could ever be solved. Antimatter propulsion represents the theoretical maximum of energy density, converting mass directly to energy with perfect efficiency. But these technologies remain decades away at minimum, if they prove achievable at all. The pattern repeats across every technological proposal examined. Each potential solution reveals its own energy inputs, infrastructure requirements, development timelines, and fundamental limitations. None offers a shortcut around the basic accounting that physics demands. Propulsion is not separate from the energy problem. Propulsion is the energy problem expressed through the mathematics of motion. Every technology that promises to solve propulsion challenges ultimately requires energy inputs that create their own limitations. We have exhausted the known possibilities that could function within reasonable development timelines. Chemical rockets lack sufficient energy density. Ion engines require power sources that fail in the outer solar system. Nuclear thermal propulsion improves efficiency, but does not provide sustained electrical power. Solar sails become useless beyond Jupiter. Advanced nuclear electric systems remain far from flight-ready and would still face daunting energy requirements. The aerospace community continues developing improved propulsion technologies. Each advance makes certain missions more achievable. Mars becomes more accessible. Asteroid mining becomes more practical. The inner solar system opens to expanding human activity, but the outer solar system remains fundamentally different. The distances are not merely larger, they are categorically larger, in ways that transform the nature of the challenge. Improvements that matter enormously for reaching Mars provide only marginal benefits for reaching Pluto. This assessment leads to an uncomfortable conclusion about human exploration of the outer solar system. The propulsion technologies we have do not work for crewed Pluto missions. The propulsion technologies we are developing will not work either. Even the propulsion technologies we can theoretically imagine face energy constraints that prevent practical application within foreseeable timeframes. The barrier is not insufficient cleverness. The barrier is physics itself. The energy required to move human beings and their life support systems to Pluto and back exceeds what any known or near-term propulsion technology can provide within reasonable mission durations. Yet propulsion represents only half the energy equation for a crewed mission. Moving the spacecraft is one challenge. Keeping the humans inside it alive presents another challenge entirely. one that demands continuous energy expenditure throughout a journey spanning decades in the cold darkness beyond the sun's warming reach. The vacuum of space holds no air. This obvious fact carries consequences that compound across every system required to sustain human life beyond Earth. Every breath an astronaut takes comes from oxygen produced, recycled, or stored within the spacecraft. Every exhale releases carbon dioxide that must be removed before it accumulates to toxic levels. The processes that manage this atmospheric balance run on electricity. Continuously, for every second of the mission, a human being at rest consumes approximately 250 milliliters of oxygen per minute. During physical activity, that consumption can triple or quadruple. 6 astronauts breathing for 20 years consume roughly 1.6 million liters of oxygen. Storing that volume as compressed gas would require tanks weighing hundreds of tons. Storing it as liquid oxygen reduces mass, but introduces cryogenic handling challenges across decades of travel. The only practical solution involves recycling. Extract oxygen from carbon dioxide exhaled by the crew. Split water molecules through electrolysis to release oxygen atoms. Capture and reprocess atmospheric gases rather than venting them to space. These closed-loop systems transform a consumables problem into an energy problem. Trading mass for power requirements. The International Space Station regenerates its atmosphere through a system called the Environmental Control and Life Support System. Electrolysis units split water molecules into oxygen for breathing and hydrogen that gets vented to space or used in other chemical processes. Carbon dioxide scrubbers remove exhaled gas using chemical absorbents and zeolite molecular sieves. Trace contaminant control assemblies remove harmful gases that accumulate from equipment off-gassing, cleaning products, and human metabolism. These systems consume approximately 12 kilowatts of electrical power on the space station during normal operations. The number sounds modest compared to the station's total power generation capacity. But remember that a Pluto-bound spacecraft could not rely on solar collection. Every watt of life support power would need to come from onboard generators, fueled by material carried from Earth. The station's atmospheric systems represent decades of engineering refinement. Early spacecraft used entirely consumable systems, carrying all oxygen in tanks and absorbing carbon dioxide with lithium hydroxide canisters that could not be regenerated. The Mercury and Gemini capsules operated this way for missions lasting hours to days. Apollo extended the approach for the 2-week lunar missions. Longer duration Skylab and Mir missions began incorporating partially regenerative systems. The space station pushed further toward closure, recycling much of its atmosphere rather than consuming stored supplies. Each step toward a closed loop required more sophisticated equipment, more power, and more maintenance. A Pluto mission would need to achieve nearly complete closure, since no resupply missions could deliver fresh consumables. Every percentage point of inefficiency translates directly into mass that must be carried from Earth. The engineering challenge intensifies with each incremental improvement toward perfect recycling. The space station's atmospheric systems also benefit from regular maintenance and resupply impossible on a Pluto mission. Zeolite beds eventually saturate and need replacement. Electrolysis cells degrade over time. Fans, pumps, and valves wear out through continuous operation. The station receives replacement components every few months through cargo missions from Earth. A Pluto-bound spacecraft would need to carry every replacement part it might need for 20 or more years of operation. Redundant systems would require redundant spares. Critical components might need triple or quadruple backups. Each spare part adds mass that the rocket equation transforms into additional propellant requirements. The probability mathematics of long-duration missions work against reliability in troubling ways. A component with 99% reliability over 1 year has only 82% reliability over 20 years. A system requiring 10 such components to function has barely 14% probability of avoiding any failures over 2 decades. Redundancy helps, but cannot eliminate risk entirely. Submarine crews face similar isolation challenges, though on far shorter timescales. Nuclear submarines routinely deploy for 3 to 6 months without surfacing or receiving supplies. The crews number over 100 personnel operating sophisticated life support in a sealed environment. Yet submarines can surface in emergencies. They can reach port within days if critical systems fail. A spacecraft bound for Pluto has no such option. Antarctic research stations provide another imperfect analogy. Winter crews at the South Pole spend 8 to 9 months isolated from resupply, surviving in conditions that kill unprotected humans within minutes. But Antarctica has breathable air. Stations can stockpile years of frozen food. Emergency evacuation, while extremely difficult in winter, remains theoretically possible. A Pluto crew would face isolation measured in decades, not months, with no possibility of emergency return. The Biosphere 2 experiment in the early 1990s attempted to create a completely closed ecological system on Earth. The project encountered unexpected problems with atmospheric composition, food production, and social dynamics among the crew. Carbon dioxide levels fluctuated unpredictably. Oxygen levels dropped enough to impair cognitive function. The project required external intervention multiple times, despite being located in the Arizona desert with hospitals minutes away. But atmospheric management represents only one dimension of keeping humans alive. Water represents another critical requirement that compounds the energy challenge in unexpected ways. The average human needs roughly 3 liters of drinking water per day under normal conditions. Astronauts in microgravity may need slightly less due to fluid redistribution effects, but the requirement remains substantial. Physical exertion increases water needs. Illness increases water needs. The spacecraft's air processing systems require water for electrolysis. Hygiene requires water. Food preparation requires water. For a crew of 6 on a 20-year round-trip mission, drinking water alone totals approximately 130,000 litres. Adding hygiene, food preparation, and system requirements might double or triple that figure. 300,000 litres of water masses. 300 metric tons before counting any containers, pumps, filters, or distribution systems. Carrying 300 metric tons of water from Earth would be catastrophically expensive in propulsion terms. The rocket equation transforms those 300 tons into thousands of additional tons of propellant needed to accelerate the water to interplanetary velocities and then decelerate it at the destination. Water recycling provides the only practical solution. The space station's water recovery system processes urine, sweat, humidity condensate from the atmosphere, and other wastewater back into potable water. The current system achieves approximately 93% efficiency. Each cycle recovers most but not all of the water, with losses requiring occasional resupply from Earth. A Pluto mission would need to achieve even higher recycling efficiency, since no resupply missions could reach a spacecraft in the outer solar system. Closing the loop to 98 or 99% recovery would require more sophisticated filtration, more processing stages, more power for distillation and purification, and more redundancy to guard against failures that could strand the crew without water billions of miles from help. Even at 99% efficiency, a 20-year mission would lose approximately 3,000 litres of water through system inefficiencies, airlock operations, and unavoidable leakage. Backup reserves must cover these losses, plus account for potential system failures that might contaminate or lose larger quantities. The power requirements for water recycling on the space station hover around 4 kilowatts during normal operations. More aggressive recycling targeting higher efficiency would require additional power for extra processing stages. Backup systems, sitting ready for activation, add mass, even when not consuming power. Food introduces its own cascade of requirements that ultimately trace back to energy constraints. Astronauts on the space station consume pre-packaged meals launched from Earth on regular resupply missions. The food arrives freeze-dried, thermostabilized, or irradiated for preservation. Crew members add water to rehydrate dried foods and heat meals using onboard warming equipment. Fresh fruits and vegetables arrive occasionally as treats, consumed quickly before spoilage occurs. Each crew member needs roughly 1.8 kilograms of food per day to maintain health and performance. This figure accounts for the caloric and nutritional needs of adults performing light to moderate physical activity in a controlled environment. For 6 astronauts over 20 years, daily food consumption totals approximately 79,000 kilograms. 79 metric tons of food, plus packaging materials that might add 20 to 30% to that mass. Plus storage containers designed to maintain food quality across decades. Plus heating equipment to prepare meals. Plus refrigeration systems where needed for items requiring cold storage. Plus the water and atmospheric systems already discussed. Plus propulsion fuel to move all of this mass across billions of miles. The mass burden becomes staggering before accounting for the degradation problem. No preserved food maintains nutritional quality indefinitely. Vitamins break down over time, fats go rancid, proteins denature. Even the best preservation techniques cannot prevent slow deterioration across 20-year timescales. Vitamin C degrades particularly rapidly, losing significant potency within years, even under ideal storage conditions. B. Vitamins show similar instability. A crew relying on 20-year-old provisions might develop deficiency diseases despite consuming adequate calories. Scurvy, beriberi, and pellagra plagued sailors on long voyages in previous centuries. A Pluto crew could face similar fates from degraded nutrients. Food scientists have extended shelf life significantly through advances in processing and packaging. Military rations maintain acceptability for 5 to 7 years under proper storage conditions, but acceptability differs from optimal nutrition. A crew eating 20-year-old food might survive while suffering deficiencies that degrade health and performance. Growing food on board might reduce launch mass by producing fresh calories during the journey, rather than carrying preserved provisions from the start. Space agriculture experiments on the station have successfully grown lettuce, radishes, peppers, and other crops in controlled environments. NASA's veggie and advanced plant habitat systems demonstrate that plants can be cultivated in microgravity using LED lighting and carefully controlled nutrient delivery. But food production in space requires substantial energy inputs. Plants need light for photosynthesis. The specific wavelengths that drive plant growth most efficiently fall in the red and blue portions of the visible spectrum. Modern LED systems can target these wavelengths precisely, converting electrical energy into photosynthetically active radiation more efficiently than traditional lighting. At Pluto, no useful sunlight reaches the spacecraft. Every photon driving plant growth must come from LED arrays powered by onboard generators. A meaningful food production capability might require tens of kilowatts dedicated solely to grow lights operating continuously. The caloric mathematics work against space agriculture for a Pluto mission. Current space farming techniques produce perhaps 1 to 2 kilograms of edible plant material per square meter per month under optimal conditions. Feeding 6 people requires roughly 300 kilograms of food per month. Providing even half of crew calories through onboard agriculture would require growing areas measured in hundreds of square meters, each demanding continuous artificial lighting. The energy cost per calorie produced exceeds the energy cost of carrying preserved food by substantial margins. Space agriculture makes sense for supplementing preserved rations with fresh produce, improving crew morale and providing certain vitamins. It does not make sense as a primary food source given current technology's energy efficiency. Medical care presents challenges that interact with energy requirements in complex ways. A crew traveling for decades cannot avoid all illness and injury. Infections occur. Accidents happen. Cancer risk increases from radiation exposure, The normal processes of aging continue regardless of location. Earth-based hospitals rely on vast infrastructure. Diagnostic imaging requires CT scanners, MRI machines, and X-ray equipment consuming substantial power. Surgery demands sterilization equipment, monitoring systems, anesthesia machines, and recovery facilities. Pharmacies stock thousands of medications with varying shelf lives and storage requirements. A Pluto spacecraft cannot carry a full hospital. The mass penalty would be prohibitive. Instead, mission planners must select medical capabilities carefully, balancing probability of need against mass and power costs. Basic surgical capability might be essential. Advanced imaging might be sacrificed. Pharmaceutical stocks would be limited to the most likely needed medications. Telemedicine consultations with Earth-based physicians could provide diagnostic support and treatment guidance, but communication delays of 10 hours round trip make real-time consultation impossible. A medical emergency requiring immediate decisions would have to be handled by crew members with whatever training and equipment they carried. The power requirements for medical systems vary widely depending on capability level. A basic sick bay with diagnostic monitors, refrigerated medication storage, and surgical lighting might require 5 to 10 kilowatts. More advanced capabilities would demand proportionally more power. This brings us to thermal control, perhaps the most energy-intensive aspect of life support in the outer solar system. Space is cold in a very specific way that differs from cold on Earth. The cosmic microwave background radiation that permeates the universe corresponds to a temperature of approximately 2.7 Kelvin, just a few degrees above absolute zero. An object in deep space with no internal heat source and no exposure to stellar radiation would eventually cool toward this background temperature. But objects in space do not lose heat through conduction or convection as they would in an atmosphere. Heat loss occurs only through radiation, the emission of infrared photons from the object's surface. Hotter objects radiate more intensely than cooler objects, according to the Stefan Boltzmann law. Spacecraft in Earth orbit stay warm, primarily because sunlight continuously heats their sun-facing surfaces. The intensity of solar radiation at Earth's distance from the Sun measures approximately 1,360 watts per square meter. This energy input balances against radiative losses from the spacecraft's surface, establishing equilibrium temperatures that depend on surface properties and geometry. At Pluto's distance, the Sun provides essentially no useful heating. A spacecraft receives negligible thermal input from the distant Sun. The spacecraft floats in darkness so profound that its exterior surfaces would rapidly cool toward cryogenic temperatures without active thermal management. Electronic components fail at low temperatures. Semiconductors stop conducting properly, batteries lose capacity, and can suffer permanent damage. Lubricants in mechanical systems solidify, jamming gears and bearings. Seals become brittle and crack. Propellants can freeze in fuel lines. Sensors drift out of calibration. Human tissue freezes at temperatures only slightly below the normal body temperature range. The proteins and lipids that comprise cellular machinery lose function as temperatures drop. Hypothermia becomes life-threatening long before actual freezing occurs. Everything on a crewed spacecraft bound for Pluto requires temperatures far above the ambient environment. Crew compartments must maintain roughly 20 degrees Celsius. Electronics typically require temperatures above -40 degrees Celsius and below, plus 50 degrees Celsius for reliable operation. Propellant systems may need specific temperature ranges, depending on the propellants used. Maintaining these temperatures requires either passive insulation to retain internally generated heat or active heating systems that consume power. Most practical designs combine both approaches. Multi-layer insulation consists of thin reflective films separated by low conductivity spacers. The reflective layers bounce thermal radiation back toward the spacecraft rather than allowing it to escape to space. Properly designed multi-layer insulation can reduce radiative heat loss by factors of 100 or more compared to bare surfaces, but no insulation is perfect. Heat leaks through structural connection points where insulation cannot be applied. Windows and observation ports required for navigation or crew. Psychological health conduct heat directly to space. Airlocks and docking ports create thermal bridges to the exterior. A crewed spacecraft would generate substantial waste heat from equipment operation and human metabolism. Each human body generates roughly 100 watts of thermal energy at rest. Equipment operation adds hundreds or thousands of watts depending on activity levels. This waste heat could potentially maintain temperatures if insulation were perfect and all systems operated normally. The problem emerges from the mismatch between heat generation and heat loss pathways. Heat must be moved from where it is generated to where it is needed, or where it can be safely rejected. This thermal management requires pumps, heat exchangers, and control systems that consume power. The International Space Station actually struggles with the opposite problem in Earth orbit. Abundant sunlight and continuous equipment operation generates so much heat that massive radiator panels must dump excess thermal energy into space. At Pluto, the thermal architecture would reverse entirely. Rather than rejecting excess heat, the spacecraft would desperately retain every watt of thermal energy generated internally. Engineering studies estimate heating requirements at Pluto distances range from 20 to 50 kilowatts, depending on spacecraft design choices. Larger spacecraft with more surface area lose heat faster and require more heating power. The thermal control requirement alone matches or exceeds the power needed for all other life support functions combined. Physical fitness presents another energy-dependent challenge for long-duration spaceflight. In microgravity, human bodies deteriorate rapidly without countermeasures. Bones lose calcium at rates of 1 to 2% per month. Muscles atrophy from disuse. Cardiovascular systems weaken as hearts no longer pump against gravity. Astronauts on the space station exercise approximately 2 hours daily using specialized equipment. Treadmills with harness systems simulate running against gravity. Resistance machines using vacuum cylinders or flywheel mechanisms provide weightlifting equivalents. Stationary bicycles maintain cardiovascular fitness. This exercise equipment consumes power for motors, displays, data recording, and ventilation systems that remove heat and sweat vapor from around exercising crew members. The power requirements are modest compared to other life support systems, perhaps 1 to 2 kilowatts during active use, but the equipment adds mass and complexity. Without rigorous exercise countermeasures, astronauts returning from long missions struggle to walk. Bones weakened by calcium loss fracture more easily. Muscles wasted by disuse cannot support body weight. A crew arriving at Pluto after 10 or more years in microgravity might be physically incapable of conducting surface operations, even in Pluto's weak gravity. Some mission concepts propose artificial gravity through spacecraft rotation. A rotating habitat would create centrifugal force that mimics gravity, potentially eliminating or reducing the physiological deterioration of microgravity. But rotating spacecraft add mechanical complexity, require more robust structures to handle rotational stresses, and introduce challenges for docking, communication, antenna pointing, and propulsion system orientation. The energy cost of maintaining rotation is minimal once established, but the structural mass penalty could be substantial. Whether artificial gravity systems would save or cost energy overall depends on detailed design trade-offs that have not been fully explored. Add up the pieces accumulated so far. Atmospheric processing requires roughly 12 kilowatts. Water recycling needs 4 kilowatts. Food storage, preparation, and supplemental growing requires perhaps 8 kilowatts. Medical systems need 5 to 10 kilowatts. Thermal management demands 20 to 50 kilowatts. Communication systems require several kilowatts for transmitting signals across billions of miles. Navigation computers, attitude control, and housekeeping systems require additional kilowatts. Exercise and fitness systems add another few kilowatts during use. A crewed spacecraft at Pluto might need 70 to 100 kilowatts of continuous electrical power simply to maintain basic life support, without any allocation for propulsion systems, scientific equipment, manufacturing capabilities, or backup reserves. 100 kilowatts. Continuously, for 20 or more years, without interruption, without the possibility of repair from Earth, without resupply, without any external assistance whatsoever. The largest radioisotope thermoelectric generators ever flown in space produced roughly 300 watts at beginning of life, declining over time as the plutonium fuel decays. Meeting 100 kilowatt life support requirements would require more than 330 such units. But this arithmetic collapses against material constraints. Each generator requires several kilograms of plutonium-238. The United States currently produces approximately 1.5 kilograms of this isotope per year. Russia historically produced similar quantities. Total global production capacity cannot exceed a few kilograms annually without massive infrastructure investment. Accumulating 1,000 kilograms of plutonium-238, the amount needed for hundreds of generators, would require centuries at current production rates. Even aggressive expansion of production facilities would require decades to generate sufficient material. The scarcity of suitable radioisotope fuel eliminates this approach for crewed missions regardless of other engineering considerations. Space-rated nuclear fission reactors capable of 100 kilowatt output have been designed on paper but never flown or even fully prototyped. The Soviet Union tested the Topaz reactor series in orbit with outputs around 5 kilowatts. American programs developed the SNAP series reactors, reaching similar power levels. Both nations abandoned space reactor programs decades ago. Recent American efforts under the Kilopower project demonstrated a 10 kilowatt reactor core in ground testing. Scaling from 10 kilowatts to 100 kilowatts introduces engineering challenges that have not been addressed. But the reactor itself only begins the accounting. Nuclear reactors produce thermal energy that must be converted to electricity through some thermodynamic cycle. Current space reactor designs achieve conversion efficiencies of roughly 25 to 30%. The remaining 70 to 75% of nuclear thermal energy becomes waste heat that must be radiated to space. Radiator systems for a 100 kilowatt electrical output might require surface areas measuring hundreds of square meters depending on the operating temperature of the power conversion cycle. Those radiators add mass. That mass requires propellant to accelerate. The propellant adds more mass. The structural systems to support deployed radiators add mass. The system of constraints tightens with every additional requirement. Radiation exposure represents another life support challenge that interacts with energy requirements through shielding and active protection approaches. Beyond Earth's protective magnetic field, interplanetary space seethes with charged particles from two primary sources. Solar particle events release bursts of protons and heavier ions during flares and coronal mass ejections. These events occur unpredictably and can deliver dangerous radiation doses within hours. Galactic cosmic rays arrive continuously from outside our solar system. These particles include protons and heavy ions, accelerated to extreme energies by distant astrophysical processes. Unlike solar particles, galactic cosmic rays cannot be predicted or avoided. They permeate interplanetary space at roughly constant intensity. Both radiation sources cause cumulative damage to human tissues. Ionizing radiation breaks chemical bonds in DNA, potentially causing cancer or genetic damage. High-energy particles can kill cells directly or trigger inflammatory responses. Long-term exposure increases cancer risk substantially and may cause cognitive effects that impair crew performance. A Pluto mission would expose crew members to continuous galactic cosmic radiation for 20 or more years. Without protection, cumulative doses would far exceed any established safety limits. Passive shielding materials block radiation through absorption and scattering. Hydrogen-rich materials work best because hydrogen nuclei interact strongly with incoming particles. Water provides excellent shielding and serves multiple purposes if placed in tanks surrounding crew quarters. Polyethylene and other hydrogen-rich plastics offer similar protection with different structural properties. Effective shielding for a multi-year mission might require mass equivalent to several centimeters of aluminum surrounding all habitable areas. This translates to tens of metric tons of shielding material that must be accelerated to interplanetary velocities and decelerated at the destination. Active magnetic shielding has been proposed as an alternative that might weigh less than passive approaches for equivalent protection. Superconducting magnets could generate intense magnetic fields that deflect charged particles around the spacecraft. The concept faces significant engineering challenges. Superconducting magnets require cryogenic cooling to maintain their superconducting state. Power requirements for the cooling systems would add to life support loads. Neither shielding approach is free in energy terms. Psychological factors represent yet another dimension of crew survival that connects to energy through multiple pathways. Humans are social creatures evolved for life in communities with varied environments, changing seasons, and regular contact with the natural world. A spacecraft traveling to Pluto offers none of these comforts. The crew would spend 20 years in a confined space roughly the size of a small house, seeing the same faces every day, eating the same limited menu, exercising on the same equipment, breathing the same recycled air. Earth would shrink to a pale blue dot, indistinguishable from countless other stars. Communications with family and friends would be delayed by hours, making normal conversation impossible. Studies of isolated populations consistently find elevated rates of depression, anxiety, interpersonal conflict, and cognitive degradation. Antarctic winter crews show measurable psychological effects after just a few months of isolation. Submarine crews require careful screening and support to maintain function during deployments of several months. Addressing psychological needs requires energy expenditure. Varied lighting that simulates natural daylight cycles requires programmable LED systems consuming power. Entertainment and communication systems require electrical support. Climate variations that break monotony require thermal control flexibility. Private spaces where crew members can retreat from social pressures require additional volume that adds structural mass. The alternative to providing psychological support is accepting degraded crew performance and elevated risk of interpersonal conflict. Neither option is free. Cryogenic hibernation appears frequently in science fiction as a solution to long-duration space travel challenges. If crew members could be placed in suspended animation, their metabolic needs would drop dramatically. A sleeping body requires far less oxygen, produces less carbon dioxide, needs no food, and generates minimal waste heat. The concept has superficial appeal because it appears to address multiple problems simultaneously. Reduce crew metabolism, and you reduce atmospheric processing requirements, water consumption, food needs, and psychological stress from isolation. Reality proves more stubborn than fiction. No human has ever been placed in true suspended animation and successfully revived. The biological mechanisms that might enable safe, long-term hibernation remain poorly understood and far from clinical application. Medical-induced hypothermia can reduce metabolic rates for limited periods during surgery or after cardiac arrest. Cooling the body to 32 or 33 degrees Celsius slows cellular processes and reduces oxygen demand. But this technique operates on timescales of hours, not years. Even if hibernation technology were perfected through some future breakthrough, it would not eliminate energy requirements. Hibernating bodies still need life support, just reduced life support. Temperatures must be precisely maintained. Atmospheric composition must prevent both oxygen deprivation and carbon dioxide accumulation. Medical monitoring systems must track vital signs continuously. Hibernation might reduce crew energy requirements by 50% or more if it worked perfectly. but 50% of an overwhelming number remains overwhelming. Generational ships represent another concept proposed for extremely long-duration missions. If the journey required multiple decades, perhaps multiple generations of crew could live and die during transit. Children born in space would eventually replace their parents, maintaining the mission across timescales exceeding individual human lifespans. This approach addresses biological limits of human lifespan, but multiplies every other requirement substantially. More people means more food, more water, more oxygen, more waste processing, more living space, more medical facilities, more recreational facilities, more educational resources for children growing up aboard. Energy demands scale with population. A ship supporting 500 people requires roughly 80 times the life support power of a ship supporting 6. The mass penalties cascade through the rocket equation, with devastating effects on propellant requirements. Every approach to keeping humans alive in deep space amplifies the energy problem rather than solving it. Reduce one requirement, and others grow to compensate. Introduce new technologies, and they bring their own power demands. Extend mission duration and component failure rates. Force additional redundancy. All of this collapses under one constraint that refuses to yield to clever engineering. Energy determines what is possible in space. The outer solar system receives no useful solar energy. Nuclear power sources capable of sustaining human life for decades remain undeveloped. Every alternative faces fundamental limitations rooted in physics rather than engineering. The International Space Station, representing humanity's most sophisticated life support system ever built, requires constant resupply from Earth, draws power from abundant solar energy, orbits within Earth's protective magnetic field, and supports its crew barely 200 miles above the surface where emergency return remains possible within hours. A Pluto mission would have none of these advantages. No resupply for consumables or spare parts, no solar power in any useful quantity, no magnetic field protection from radiation, no possibility of emergency return for any emergency. Journey times measured in decades rather than days. The spacecraft must carry everything it needs from departure to return. It must produce its own power continuously for longer than most human-engineered systems have ever operated. It must maintain all critical systems without failure or with sufficient redundancy to survive any failure that occurs. The question becomes not whether we can keep humans alive at Pluto in some abstract theoretical sense. The question is whether we can generate enough energy, sustainably, for long enough, to make survival possible within any reasonable constraints. Life support for a crewed Pluto mission requires 70 to 100 kilowatts of continuous electrical power for 20 or more years. This power must come from sources that can operate reliably for decades without resupply or major maintenance. No such sources currently exist in flight-ready form, and life support represents only half the energy equation. The propulsion requirements documented in earlier sections demand their own massive energy inputs. The total mission energy budget combines both requirements into figures that must now be confronted directly. Now we confront the ultimate calculation. Every challenge discussed in previous sections, the vast distances, the propulsion limitations, the relentless life support demands, all reduced to a single question that will determine whether humans can ever stand on Pluto's frozen surface. How much energy does a crewed mission to Pluto actually require, and does humanity possess any means of providing it? The answer emerges through careful accounting. Every system, every requirement, every technical challenge converts into energy units that can be summed and compared against what we can realistically produce. The mathematics are unforgiving. They do not respond to optimism or ambition. They simply reveal what physics demands. Begin with propulsion, the challenge of moving mass across billions of miles. A crewed spacecraft carrying 6 astronauts, their life support systems, scientific equipment, consumables, and supplies for a 20-year round-trip mission might mass approximately 500 metric tons in its final operational configuration. This estimate draws from engineering studies of proposed Mars transit vehicles, scaled upward substantially to account for the longer duration, greater consumable requirements, and additional redundancy that a Pluto mission would demand. 500 metric tons represents roughly 5 times the mass of the International Space Station. Building and launching such a vehicle would require multiple heavy-lift rockets, orbital assembly operations spanning years, and testing programs exceeding anything previously attempted in space exploration history. Moving 500 metric tons from Earth orbit to Pluto orbit and back requires velocity changes, totaling roughly 30 kilometers per second. This figure accounts for escaping Earth's gravitational influence, transferring to a trajectory toward the outer solar system, matching velocities with Pluto for orbital insertion or landing, and reserving capacity for course corrections, emergency maneuvers, and the return journey home. 30 kilometers per second of total velocity change represents an enormous propulsion requirement. For comparison, reaching low Earth orbit requires approximately 9.4 kilometers per second. The Apollo missions to the Moon required roughly 16 kilometers per second total. A round trip to Mars might require 12 to 16 kilometers per second, depending on trajectory choices. The Pluto mission demands roughly double the velocity change of any crewed mission ever seriously planned. The rocket equation transforms velocity requirements into propellant mass through exponential mathematics. With nuclear thermal propulsion at exhaust velocities around 9 kilometers per second, a 500 metric ton payload would require over 60,000 metric tons of hydrogen propellant. The mass ratio exceeds 120 to 1. 60,000 metric tons of liquid hydrogen propellant present storage challenges that approach the impossible for a multi-decade mission. Hydrogen boils at 20 degrees above absolute zero. Keeping it liquid requires either massive insulation systems that add further mass or continuous refrigeration that consumes continuous power. Boil-off losses over 20 years would consume substantial fractions of the propellant supply, regardless of insulation quality. The energy contained in propellant represents the first major entry in our accounting ledger. 60,000 metric tons equals 60 billion kilograms. Multiplying yields approximately 800 petajoules for propulsion alone. 800 petajoules. For perspective, a typical nuclear power plant generates roughly 1 gigawatt of electrical power. Running such a plant continuously for 1 year produces approximately 31 petajoules. The propulsion energy for a Pluto mission equals roughly 25 years of output from a large nuclear power plant. Now add life support requirements. 100 kilowatts of continuous electrical power for 20 years translates directly into energy units. 100 kilowatts times 20 years times 365 days per year times 24 hours per day equals 17.5 million kilowatt hours. Converting to joules yields approximately 63 petajoules of electrical energy required for life support alone, but electrical energy must be generated from primary energy sources with substantial efficiency losses. Nuclear fission reactors convert thermal energy into electricity through thermodynamic cycles, achieving roughly 25 to 30% efficiency. A reactor system producing 63 petajoules of electricity over 20 years requires roughly 250 petajoules of nuclear fuel energy when accounting for conversion efficiency. The uranium or other fissile material must contain this energy in nuclear binding forces, ready for controlled release throughout the mission. Total mission energy accounting thus far approaches 1,000 petajoules when combining propulsion and life support requirements. 1,000 petajoules equals 1 exajoule. For comparison, all of human civilization consumed approximately 580 exajoules of primary energy in 2022. This includes all electricity generation, transportation fuels, industrial processes, heating, and every other energy use across the entire planet for an entire year. The Pluto mission would require energy equivalent to roughly 0.1% of annual global energy consumption. That fraction might sound encouragingly small, Surely humanity could dedicate such a modest portion of its energy budget to an ambitious space mission. This optimism dissolves upon examining how the energy must be delivered. 1,000 petajoules stored as coal cannot propel a spacecraft. The energy must be converted into specific forms compatible with space operations. It must be packaged as rocket propellant and nuclear fuel. It must be launched into orbit, assembled into spacecraft systems, and carried across billions of miles in configurations that remain functional for decades. The conversion efficiencies involved slash those manageable sounding percentages into oblivion. Consider nuclear fuel production in detail. Enriched uranium does not occur naturally in forms suitable for reactor fuel. Natural uranium contains only 0.7% of the fissile isotope, uranium-235. The remaining 99.3% is uranium-238, which does not sustain chain reactions in conventional reactor designs. Enrichment processes separate these isotopes through energy-intensive methods. Gaseous diffusion plants consume enormous electrical power. Centrifuge facilities spin uranium compounds at tremendous speeds. Both approaches require substantial energy inputs per unit of enriched product. Space nuclear systems typically require higher enrichment levels than commercial reactors. The uranium fuel for a multi-megawatt space reactor might require enrichment to 50% or higher, uranium-235 concentration. Producing such fuel in quantities sufficient for a 20-year mission would consume substantial fractions of global enrichment capacity for extended periods. Now consider the manufacturing energy for the spacecraft itself. Building 500 metric tons of flight hardware requires mining raw materials, refining ores into metals, fabricating components to exacting tolerances, assembling systems through careful integration, and testing everything exhaustively. Space-grade equipment demands precision manufacturing with energy intensities far exceeding ordinary industrial production. Estimates for spacecraft manufacturing energy range from 100 to 500 megajoules per kilogram of finished flight hardware. For 500 metric tons, this translates to another 50 to 250 petajoules of industrial energy consumption before the mission even leaves Earth. Assembly in orbit adds further requirements. Each kilogram of payload delivered to low Earth orbit costs approximately 13 gigajoules of launch energy when accounting for propellant, manufacturing of expendable rocket stages, and ground infrastructure operations. 500 metric tons of final spacecraft might require 5,000 metric tons of total launch mass when accounting for orbital assembly equipment, construction spacecraft, and structural margins. 5,000 metric tons times 13 gigajoules equals 65 petajoules just for launch energy. The accounting continues expanding with each additional consideration. Mission control infrastructure on Earth must operate continuously for 20 or more years. Ground stations for deep space communication require substantial electrical power. Training programs, simulation facilities, and backup systems all require energy inputs. None of these additions individually transform the energy requirements from possible to impossible, but collectively they demonstrate that the simple propellant calculation vastly understates the true energy cost. The 1,000 petajoules calculated earlier might represent only the direct mission energy, with total program energy requirements potentially several times larger, and we have not yet addressed perhaps the most fundamental constraint. The energy must be available in the right forms, at the right times, stored in configurations that actually work for space operations. Terrestrial energy infrastructure cannot help a spacecraft traveling billions of miles from Earth. Automation and robotics appear frequently in discussions of reducing crewed mission requirements. If machines can replace human functions, perhaps life support demands could be eliminated entirely. Send sophisticated robots instead of fragile human beings. New Horizons already demonstrated that robots can reach Pluto. The spacecraft operated successfully with roughly 200 watts of power, a factor of 500 less than crewed mission requirements. It captured detailed photographs, measured atmospheric composition, mapped surface features, and transmitted data back to Earth. By most scientific measures, the mission succeeded completely. If scientific knowledge represents the purpose, robots achieve those goals far more efficiently than human crews could ever accomplish. But even robotic missions face energy constraints that limit capabilities far below what we might wish. New Horizons performed a flyby because it lacked energy to stop. A robotic orbiter at Pluto would need propulsion energy scaled down from crude requirements, but still enormous compared to flyby missions. A robotic surface mission would face even more severe energy challenges. The gap between flyby and meaningful sustained presence remains vast regardless of whether humans travel along. Automation reduces life support requirements to zero, but does not change propulsion physics. The rocket equation applies equally to robots and humans. Robotic missions also cannot satisfy the human ambitions that drive exploration beyond mere data collection. The question posed at the beginning asked how long it would take us to reach Pluto, with the implicit assumption that us means human beings standing on alien ice. That aspiration requires facing the full energy accounting without shortcuts. So, where might sufficient energy come from, if not from current sources? Antimatter represents the most energy-dense fuel theoretically possible within known physics. When matter and antimatter annihilate, they convert 100% of their combined mass into energy. A single gram of antimatter reacting with a gram of normal matter releases approximately 90 trillion joules. A Pluto mission requiring roughly 1,000 petajoules would need approximately 5.5 metric tons of antimatter. This mass sounds feasibly transportable compared to 60,000 metric tons of hydrogen propellant. The insurmountable problem lies not in using antimatter, but in creating it. Total human antimatter production throughout history amounts to roughly 20 nanograms. Particle accelerators around the world have collectively manufactured approximately 20 billionths of a gram since the technology became available. Producing 5.5 metric tons would require scaling up production by a factor of approximately 10 to the 17th power. Current antimatter production consumes vastly more energy than the antimatter contains. The efficiency of the best production methods runs roughly 1 billionth. Creating 1 gram of antimatter requires approximately 1 billion grams equivalent of input energy. Producing 5.5 metric tons of antimatter would demand energy inputs exceeding all energy humanity has ever produced throughout recorded history. The total energy consumption of human civilization, from the first fires to the present day, would not suffice to manufacture the antimatter for a single Pluto mission. Antimatter propulsion fails not because the physics is wrong, but because the energy required to create antimatter makes the entire concept circular. You need energy to make the fuel. You need more energy than the fuel contains by factors of billions. The accounting never closes. Nuclear fusion presents a somewhat less extreme case, but faces similar fundamental difficulties. Fusion reactions release millions of times more energy per unit mass than chemical reactions. The hydrogen isotopes that fuel fusion are abundant on Earth and throughout the solar system. Proposed fusion spacecraft could potentially achieve exhaust velocities of hundreds of kilometers per second. The engineering studies look encouraging on paper. Fusion might reduce propellant requirements to manageable levels. Fusion reactors could potentially provide both propulsion and electrical power from a single integrated system. The fuel costs would be negligible compared to fission alternatives. But fusion power plants do not exist. After more than 70 years of intensive research and hundreds of billions of dollars invested across multiple nations, no fusion reactor has ever produced more energy than it consumed. Recent experiments at the National Ignition Facility achieved fusion ignition for the first time in human history during December of 2022. The facility's laser systems delivered approximately 2.05 megajoules of energy to a fuel pellet, triggering fusion reactions that released approximately 3.15 megajoules. For the first time, a controlled fusion reaction produced more energy than the energy used to initiate it. Headlines celebrated this achievement as a breakthrough toward practical fusion power. The celebration overlooked crucial context. The facility's laser systems drew their energy from an electrical grid. The total electrical energy consumed to charge and fire those lasers exceeded 300 megajoules. The facility produced roughly 1% of the energy it consumed when accounting for the complete system. Scientific break-even and engineering break-even represent vastly different thresholds. Producing fusion energy exceeding the direct trigger energy demonstrates that the physics works. Producing fusion energy exceeding total facility consumption demonstrates practical power generation. The first has been achieved. The second remains distant. A working fusion power plant suitable for terrestrial electricity generation might emerge within 2 or 3 decades if research continues and funding remains adequate. A fusion rocket engine suitable for spacecraft would require additional development beyond power plant technology. Waiting for fusion to mature means adding decades to any timeline for reaching Pluto with human crews. And fusion does not eliminate energy requirements. It potentially makes meeting them more practical. But the engineering challenges of building fusion systems that operate reliably in space for decades have barely been studied. The pattern repeats across every technological proposal examined. Each potential solution reveals its own energy inputs, infrastructure requirements, development timelines, and fundamental limitations. None offers a shortcut around the basic accounting. This brings us to the philosophical weight of what the numbers reveal. Energy constraints are not technical limitations, waiting to be overcome by cleverness, funding, or determination. They reflect fundamental properties of physical reality, encoded in the deepest laws of nature. Matter resists acceleration. Distance requires time or energy, or both. Chemical bonds contain finite energy. Nuclear reactions obey conservation laws. These are not rules that future engineers can break through superior skill. They are not obstacles that increased budgets can purchase passage around. They are the rules of the universe itself. Within these constraints, some problems yield to human effort and others do not. We have landed humans on the moon because the moon is close enough that chemical rockets suffice and missions can complete before supplies run out. We have sent robotic probes throughout the solar system because their power requirements remain modest enough for existing nuclear generators. We will likely send humans to Mars within the coming decades because the distances and durations remain within the envelope that near-term technology can address. But sending humans to Pluto operates in a different category entirely. The distances exceed Mars distances by factors of 20 to 40. The durations extend from months to decades. The energy requirements exceed current capabilities by orders of magnitude. This is not pessimism. This is arithmetic. The conclusion is not that reaching Pluto with human beings is absolutely impossible in some philosophical sense. Given unlimited timescales, unlimited resource allocation, and unlimited tolerance for risk, perhaps some future civilization utterly unlike our own could eventually accomplish it. The conclusion is that energy represents the decisive barrier, not distance measured in miles, not time measured in years, not human psychology. Energy determines possibility. Energy is what we lack in sufficient quantity and appropriate form. Every other challenge facing a Pluto mission traces back to energy when examined carefully. Propulsion limits arise from energy density. Rockets can only accelerate exhaust to velocities permitted by their energy source. Life support demands arise from the continuous energy needed to maintain biological systems far from the sun's warmth. Duration constraints arise from the energy required to achieve faster transit times. The connections form an unbreakable logical chain. Solve the energy problem, and every other challenge becomes tractable. Provide sufficient energy in appropriate forms, and propulsion works. Provide sufficient energy continuously, and life support works. Provide sufficient energy for rapid transit, and duration shrinks. Fail to solve the energy problem, and no amount of cleverness or courage matters. The best engineers cannot design spacecraft that violate conservation laws. The bravest astronauts cannot survive without power for life support. The question of how long it would really take us to reach Pluto has a clear answer rooted in physics. It would take exactly as long as the energy we could bring along would allow. No shorter and no longer. The mission duration is set by the propulsion energy available divided by the mass that must be moved. This ratio determines acceleration. Acceleration determines time. With current technology, that means multiple decades in each direction for a crewed mission. 20 years out, 20 years back. An entire human career spent in transit. With projected near-term technology, perhaps somewhat faster, advanced nuclear systems under development might reduce transit times to 15 years each way. Still a generation. With technology that does not yet exist and may never exist, perhaps faster still. But fusion propulsion does not exist. Its development timeline extends decades into an uncertain future. The more honest answer acknowledges what the numbers consistently reveal. Reaching Pluto may not be possible at all for human beings. Not today. Not in our lifetimes. Perhaps not ever. Not because the universe contains some mystical prohibition, but because the energy requirements so vastly exceed human capacity that no reasonable development scenario closes the gap. We face limits. Real limits. Not psychological limits that motivation can overcome. Not funding limits that larger budgets can transcend. Physical limits. Thermodynamic limits. Energy limits that emerge from the fundamental structure of reality. The universe contains boundaries that ambition cannot cross, and technology cannot breach. The speed of light represents one such boundary. The laws of thermodynamics represent another. The relationship between energy, mass, and distance may represent a third that specifically constrains human access to the outer solar system. This may be one of those boundaries. Pluto may lie on the wrong side. The distances to the outer solar system have inspired generations of dreamers to imagine human voyages beyond the familiar inner planets. Science fiction depicts colonies on Pluto, mining operations in the Kuiper Belt, expeditions to the Oort cloud. These visions inspire and motivate. They expand our conception of human possibility. But those dreams collide with physics in calculations that produce devastating numbers. The energy required exceeds what we can produce. The forms in which that energy must be delivered do not exist. The timelines for developing adequate technology extend beyond meaningful planning horizons. Energy equals possibility. Where energy is available, things can happen. Where energy is absent, they cannot. The outer solar system represents a region where the energy availability drops so dramatically that possibilities close off one by one. When energy runs short, possibility ends. This is not philosophy. This is physics. Pluto orbits in darkness at the edge of our solar system, a tiny world of frozen nitrogen and methane circling a sun diminished to merely the brightest star in its perpetual night sky. It was discovered less than a century ago, visited by a single small robot that screamed past because it lacked the energy to stop. It will remain there, tantalizingly visible to our telescopes, probably forever beyond human reach, not because we lack the will or the vision or the courage, but because the physics simply does not work in our favor. The energy demands exceed what we can supply. The gap shows no sign of closing. Some destinations may be forever beyond us. Accepting this represents not failure, but wisdom. It is understanding the universe as it actually exists, rather than as we might wish it to be. It is recognizing that human reach, however remarkable, remains finite. The final answer to how long it would really take us to reach Pluto is this: longer than we have the energy to sustain, longer than our power sources can provide, longer than physics allows given the tools we possess or can reasonably expect to develop, and that may mean never at all. Not because we did not try, not because we did not care, but because some distances cannot be crossed with the energy available to those who wish to cross them. Pluto will keep its secrets from human eyes directly witnessing them. The frozen plains of Sputnik Planitia will not feel human footsteps. The nitrogen glaciers will flow unseen by biological observers standing on their surfaces. Our robots will continue visiting when we send them. Our telescopes will continue watching from afar. But humans standing on Pluto, looking back toward a sun shrunk to stellar insignificance, contemplating the billions of miles separating them from everything they have ever known, that image may remain forever in the realm of dreams. Beautiful dreams, inspiring dreams, but dreams constrained by an energy budget that reality refuses to expand. The universe is not cruel in setting these limits. It simply is what it is. Energy determines possibility. We have learned that lesson at every frontier humanity has ever approached. At this frontier, the lesson may be that some frontiers remain forever beyond crossing. Pluto waits in darkness, patient and cold, keeping its distance from a species that learned to dream of reaching it, but not to power the journey there.